Hello, today I talk about the chapter 29, quantum theory. The first part of the quantum theory is talk about the Planck quantum hypothesis. Um, Planck thinks energy is quantized in some systems. It means that the system don't have the continuous energy. The system only can have only the certain energy amount in it. It means it can be 1, 2, 3, 4, or 5. It can be 1.1, 1.2, 1.3, 1.4. It's not continuous. It's not a branch. So, at the result, when absorbing or emitting energy, a system only exchange a certain amount of energy, depend on the packet of energy they absorb or emitted. And while transferring energy, an atom or a molecule will absorb or emit the radiation with a certain wavelength. The main reason why the energy only had a part and don't continuous because it depends on the wavelength of the radiation. When the radiation is absorbed or emitted by a molecule. And Planck describes those energies of the radiation under frequency f is energy equal to n plus 1 over 2 total times s and time frequency f, in which s is the Planck constant. Which is equal to 6.63 times 10 minus 34 joules per second times second. Next part of this chapter is talk about the photon theory of light. The photon is defined as a quantized unit or a quantum of EM energy that is the proportion to its frequency f. EM is electric magnetic field. Magnetic energy. So, because the photon is a quantized unit, so it means the photon have an amount energy, a certain amount of energy. It's not a continuous, and the energy of the photon can be found by s time f, the Planck constant times the frequency of this photon. Not continuous. Okay, the next part is the photoelectric effect. When a photon strikes an electron in an atom or a molecule, it can transfer its energy into the electron. It means if it is an atom, something like hydrogen, with one proton and one electron here, when a photon strikes to the electron of the hydrogen, it can make hydrogen atom become H plus because the electron of the hydrogen absorb energy from the photon. And depending on the energy of the photon, electron can be moved away or excited to the next level. There are some characteristics of photon electric effect. The first one, if the electromagnetic radiation whose frequency below the threshold F0, it cannot eject electron. It means not all photons can eject electron of the hydrogen atom here. And which factor is important is the frequency. The frequency of the photon have to larger than F0, which we will know the next part of the presentation. The second is once electromagnetic radiation falls on a material, electrons are ejected without delay. It means when photon hit the electron will move away immediately. Third, the number of electrons ejected per unit of time is proportional to the intensity of the magnetic field, electromagnetic radiation. Fourth, the maximum kinetic energy of ejected electron is independent of the intensity of electromagnetic radiation. It means the kinetic energy of electron will depend on something we will know in the next part, but it's not by the intensity of the radiation. No. And the fifth, an individual photon can give all its energy to an electron. All the energy of photon hit the electron and transfer all of its energy and disappear the photon. Here is the photoelectric field, and we have the diagram which is the frequency and kinetic energy of an electron. And we have the equation to find out the kinetic energy of electron when one photon with a frequency f hit it. And here Be is the binding energy. Binding energy. If the photon don't have enough energy, this photon cannot transfer its energy into the electron. Only the photon have higher energy than the binding energy, which is depend on feature of the material. The electron will be released from the atom. The way nature of matter. The broadly wavelength consider all particles have a wavelength and create a formula to the Broglie wavelength. In here, lambda wavelength equal to the Planck constant divided by the momentum. Is momentum. So, in this definition, everything has its wave characteristic. But why we don't see the wave character in a bone or in a macroscopic things? Because this lambda is very small than its size, so we really hard to see it. Here is the structure of the orbital. One part of the chapter 29. And here the Schrödinger equation. The Schrödinger equation describing the energy of and the momentum of a wave function, where E is the total energy of the particle and psi for the time dependent wave function and psi for the time independent wave function. Here it's a little bit different. But it here and here represent for one is kinetic energy and another one is potential energy. According to the Schrödinger equation, consider electrons in an atom can stay in wave and contain certain amount of energy. It means if an electron in the 1s orbital, we will find out this orbital is around here, is orbital 1s. It will have certain energy. if the electron in the 2s orbital, the orbital of 2s is bigger, have a certain amount of energy. Similar thing if the electron in the 2p orbital, it can be the electron, maybe the orbital may be some here. Notice that the orbital of the electron is where we can find maybe 95 or 99% the electron over here. The electron stay in this orbital. It means there are another part the electron can stay outside, but it's really hard to find. This Schrodinger equation considers electrons in an atom and standing wave contain a certain energy. And with this equation, we can apply to solve several problems, like a quantum particle in the box, a simple harmonic oscillator, or a quantum barrier.